Wow, there the hotel situation is rough. Alright, I'm gonna do this. I think it's the winner. Alright, I got a room for $76 a night. Room with 7.6 stars. Is that right? $76 for 7.6 stars. I wish it was $80 for 9 stars. Alright, I guess we gotta get on the road if we're gonna get there. Oh, we're gonna have pools? Okay. I should probably get money ready. $20 bill? I mean, I have change. Should I get the smaller monies? No, I have a 20. It'll be fine. 20 in cards. I mean, let's see what happens. Hopefully, if I have to freaking Golden Gate Bridge, email, all that BS nonsense. Wait, so is this a rain holding pond? Alright, let's do this. Keyboard is away.
Fermilab, the Transcontinental Expedition goes subatomic. Live narration for driving around the Fermilab campus. I made it to Fermilab. I am driving around the campus now after touring the public areas on the bottom floor of Wilson Hall. walking through the second-floor art gallery and seeing part of the grounds. This is one of those places where you feel the institutional weight immediately. You pass through security, enter a vast federal research campus and understand that the most important thing being protected here is not merely a building or a piece of machinery. It is concentrated human knowledge. It is the accumulated brainpower of physicists, engineers, machinists, computer scientists, cryogenics specialists, electricians, technicians, architects, artists and students from across the United States and around the world. Last summer, I visited Lawrence Livermore National Laboratory in California. Fermilab gives me a related feeling: security, seriousness, huge technical systems, and the sense that the work occurring behind the visible walls matters far beyond the property line. But the missions are different. Lawrence Livermore is principally organized around national security, nuclear deterrence and related science and technology. Fermilab is America's particle physics laboratory, built to investigate the fundamental structure of matter, energy, space and time. Both demonstrate that national power is not only military hardware or political authority. National power is also the ability to gather exceptional minds, give them advanced instruments and allow them to work on problems that may take decades to understand. That is the first presidential lesson here. A country that fails to maintain its scientific institutions eventually loses the ability to understand, build and govern its own future. Wilson Hall, architecture designed for intellectual collision. The first thing that dominates this campus is Wilson Hall. From outside, it rises over the flat Illinois landscape like a modern concrete cathedral. Two immense curving towers frame a central wall of glass. From across the reflecting pond, the building looks almost like a scientific instrument itself. Two masses bending around a narrow central channel, focusing attention and movement toward the middle. Then you enter it. The exterior mass opens into a tremendous vertical atrium. Concrete balconies rise on both sides. Light enters through the enormous window and the skylights overhead. Flags from many nations hang through the space. Trees and plants occupy the center. Offices and laboratories look into the atrium, so people working on highly specialized problems remain visually connected to a much larger institution. That design was intentional. Fermilab's first director, Robert R. Wilson, believed a great laboratory required good architecture, art and a setting capable of attracting and inspiring great scientists. The building was meant to avoid regimentation while encouraging people to encounter one another and exchange ideas. Wilson Hall was also designed to be visible across the enormous campus, a physical and symbolic center for work occurring at widely separated experimental sites. It was built between 1971 and 1974 and later named for Wilson. That is not decoration added after the science. The architecture is part of the scientific system. A laboratory does not produce knowledge only because it possesses an accelerator. It produces knowledge because people with different expertise meet, compare results, argue, notice errors, improvise solutions and transfer ideas between disciplines. Wilson Hall was built to encourage that cross-pollination. The building itself is a classification and transfer node for human intelligence. People arrive with different languages, specialties, instruments and institutional backgrounds. The atrium brings them into one shared space. Conversations move between floors. Information moves from offices to laboratories, from experiments to computing systems and from one national research community to another. In Ogden, I learned that a railroad junction was not merely where tracks crossed. It required hotels, repair shops, warehouses, workers, schedules and transfer systems. Fermilab is another kind of junction. It is where theoretical physics meets precision manufacturing, where magnets meet cryogenics, where particle beams meet detectors, where engineering meets computation, where American public investment meets international scientific collaboration. And the architecture was designed to make that interaction visible. Art is not separate from the laboratory. The second-floor gallery reinforced that idea. I saw drawings that looked like entire technological landscapes, roads, beamlines, towers, machinery, energy paths and lights extending toward the horizon. I saw a drawing shaped like an immense circular funnel or vortex, as though matter, space or information were being pulled toward an invisible center. I saw iron forms placed on wood, where heavy industrial material had been transformed into something geometric and almost biological. That art belongs here. Particle physics studies things that cannot ordinarily be seen directly. Nobody stands beside a muon and looks at it with the naked eye. Scientists infer what happened through trajectories, timing, deposited energy, electrical signals, magnetic fields, statistical patterns and reconstructed events. Art performs a related translation. It takes forces, scales, structures or ideas that may be difficult to perceive and gives the human nervous system a form through which to encounter them. Robert Wilson was himself a sculptor, and one of his early hires was artist Angela Gonzalez, who helped develop the laboratory's visual identity. The second-floor art space began hosting exhibitions shortly after Wilson Hall opened and has continued as part of Fermilab's institutional culture. That is another lesson I am taking away. Science and art are not opposites. Both are methods for making invisible relationships perceptible. Science tests the relationship. Art helps us feel its scale. Architecture determines whether the people doing that work are isolated or brought into contact. A national laboratory should not be designed like a warehouse for brains. The human environment affects the work produced inside it. The accelerator is a transportation system as I drive around this campus. What becomes clear is that Fermilab is fundamentally another transportation system. It is just transporting a very different payload. The Transcontinental Railroad moved human beings, mail, coal, food and manufactured goods. The telegraph moved encoded information. Electrical grids move energy. Pipelines move fluids. Fermilab's accelerator complex moves charged particles through vacuum pipes. The scale is smaller than an atom. The speeds approach the speed of light. But the basic systems questions are remarkably familiar. What is moving? How is it accelerated? How is the route established? How sharply can it turn? What keeps it from drifting out of alignment? What happens at a transfer point? How is the payload classified? How do you know it arrived? How do you distinguish one rare event from billions of ordinary ones? The particle beam travels through a carefully controlled vacuum. The vacuum is the low-resistance operating environment, the particle equivalent of clearing obstacles from a transportation corridor. Radio frequency cavities supply energy and accelerate the particles. Magnets steer and focus the beam. Dipole magnets bend the route. Quadrupole magnets focus the particles, correcting their tendency to spread away from the desired path. Additional systems monitor position, timing, energy and beam quality. Targets transform the incoming flow into new particles. Detectors become the receiving stations that reconstruct what happened. Computing systems sort enormous amounts of information produced by those interactions. Cryogenic systems cool superconducting equipment toward absolute zero so it can produce powerful magnetic or radio frequency performance efficiently and precisely. Fermilab develops superconducting magnets and superconducting radio frequency systems not only for its own machines but for future accelerator, detector and quantum technologies. It is high-speed rail beneath matter, but it is also like aviation. A conventional train is mechanically attached to a physical track. An airplane moves freely through space but requires continuing aerodynamic forces to control its direction. A charged particle in a vacuum is not resting on a rail. It moves freely, but electromagnetic fields continually constrain and redirect its path. The magnets function almost like an invisible banked curve surrounding a vehicle moving at nearly the speed of light, and the same relationship among speed, radius and force still governs the route. The faster the particle moves, or more precisely, the greater its momentum, the more difficult it is to bend. You must increase the radius, increase the magnetic field or accept a smaller change in direction. That is exactly why high-speed passenger rail requires broad curves. The physical system cannot simply command a vehicle to make a sharp turn at extreme speed without imposing enormous sideways acceleration. A passenger train has human comfort and safety limits. A particle beam has no passengers to injure, but the route still has engineering limits. Magnetic field strength, aperture of the beam, pipe beam stability, heat radiation, energy loss, alignment tolerances, material performance, cryogenic capacity, cost. Speed does not eliminate infrastructure. Speed increases the precision demanded from the infrastructure. That is one of my biggest takeaways from Fermilab. The beamline is a right-of-way. The particle pipe is also a form of right-of-way. A railroad receives a protected strip of land because its vehicle cannot simply wander through ordinary streets. A particle beam receives a protected physical and electromagnetic corridor because the particles must be kept inside an extraordinarily narrow range of acceptable motion. The route is controlled by the beamline's geometry and field configuration. At every stage, tiny deviations matter. A train can be several inches off its expected position only by derailing catastrophically. A high-energy particle beam can drift by fractions of the available aperture and strike equipment, generate radiation or fail to reach the intended target, so the accelerator must sense, predict and correct the beam continuously. That is transportation governance at subatomic scale. There is a permitted corridor. There are operating tolerances. There are control systems. There are priority decisions. There are maintenance shutdowns. There are dispatch sequences. There are emergency protections. There are receiving stations. There are losses. There is waste heat. There is a complete circuit. mu2e, a particle scale converter searching for a forbidden route. The mu2e display may have been the most conceptually surprising part of the visit. A muon is a charged elementary particle related to the electron. It carries the same negative electric charge, but it is far heavier and unstable. Ordinarily, a muon decays into an electron and neutrinos. Energy and momentum are divided among several outgoing particles. mu2e is searching for something radically different. A muon converting directly into an electron in the field of an aluminum nucleus, without producing the neutrinos expected in ordinary decay. The experiment surrounds a thin aluminum stopping target with a large sequence of superconducting magnets. Those magnets help produce and transport a low-energy muon beam. Stop the muons in the aluminum and precisely measure the momentum of any possible conversion electrons. Fermilab says the experiment is designed to be 10,000 times more sensitive than previous searches. The system's analogy that occurred to me is a subatomic DC to DC converter. The charge remains negative. The particle identity and mass change. The much heavier muon becomes a much lighter electron. A large portion of the available rest mass energy would appear as the outgoing electron's motion, with small amounts accounted for by binding and nuclear recoil. But the analogy has an important limit. An ordinary electrical converter is expected to convert input continuously and efficiently. mu2e is not expecting every muon to become an electron through this direct process. It is searching for an event so rare that observing even a small number could reveal physics beyond the present standard model. So there are two completely different meanings of efficiency. One is energy concentration. If the event occurs, the result is a very distinctive, high-energy electron. The other is conversion probability. Nature may permit the event only extraordinarily rarely, or perhaps not at a detectable level at all. mu2e therefore needs an enormous particle supply chain. Accelerated protons production target secondary particles. Selected muons transport through curved superconducting magnets filtering and slowing aluminum stopping target. Possible conversion electron tracking and calorimetry. Computing and statistical analysis. That is not one train traveling from origin to destination. It is an intermodal particle network. Particles are created, selected, separated, redirected, slowed, stopped and measured. The experiment has to reject an overwhelming amount of ordinary activity while preserving sensitivity to one extraordinary path. That is another major national systems lesson. A breakthrough may depend less on making the desired event happen than on building a system capable of recognizing it when nearly everything else looks like noise. The same is true in government. Signals of preventable failure may be buried under millions of routine transactions. A good institution must detect the rare event before it becomes a catastrophe. Dune. A transcontinental particle line through the Earth. Then there is Dune, the deep underground neutrino experiment. This is where the second Transcontinental Expedition becomes subatomic in the most literal way. Fermilab will produce an intense neutrino beam directed toward enormous detectors approximately 1,300 kilometers, or about 800 miles, away at the Sanford Underground Research Facility in South Dakota. There is no tunnel carrying those neutrinos across the continent. Once created, neutrinos interact so weakly with ordinary matter that they can travel through the Earth itself. The experiment includes the Fermilab Accelerator Complex, a new beamline and target systems, a near detector at Fermilab, massive underground liquid argon detectors in South Dakota, cryogenic infrastructure and a worldwide computing and scientific network that will translate fleeting signals into evidence. Think about the transportation stack. A proton beam is accelerated at Fermilab. The protons strike a target. That collision produces other particles whose decay creates neutrinos. The neutrinos leave the engineered beamline and travel through roughly 800 miles of Earth. A near detector measures the beam close to its origin. The far detector measures what arrives in South Dakota. Scientists compare the two. The Earth itself becomes part of the experimental corridor. This is a transcontinental line with no visible track between its principal stations. The payload is not freight or passengers. It is a flux of elusive particles carrying evidence about the structure and history of the universe. Dune will study how neutrinos change among types, investigate differences between matter and antimatter, watch for neutrinos from an exploding star, and search for rare processes that could help explain why matter survived in sufficient quantities for galaxies, planets and human beings to exist. So this experiment is asking a foundational question. Why is there a material universe here for us to investigate at all? International collaboration at national scale. The flags inside Wilson Hall are not symbolic decoration alone. Dune and its supporting infrastructure bring together more than 1,500 scientists and engineers from over 200 institutions and more than 35 countries. Fermilab describes it as the first truly international megascience experiment hosted on American soil, with major international contributions to Dune, the Long Baseline Neutrino Facility and the PIP-2 Accelerator Project. CERN's participation includes its first investment in research infrastructure outside Europe. That is enormous. This is the United States acting as a host for world science. There is a difference between merely participating in international research and building the institution around which international research organizes itself. Hosting creates responsibilities and advantages. It requires the United States to provide reliable facilities, funding continuity, project management, visas, transportation, computing, procurement, safety systems, and confidence that a 20-year scientific commitment will not be broken by a 2-year political cycle. In return, knowledge, talent, equipment and investment flow toward the United States. Students begin their careers here. Engineers develop new capabilities here. Companies learn to manufacture difficult components. Universities build research groups around access to the facility. International scientific relationships become durable diplomatic relationships. The laboratory becomes a junction for peaceful cooperation. At a time when nations compete over semiconductors, artificial intelligence, quantum technology, energy, aerospace and advanced manufacturing, Fermilab demonstrates that international collaboration and American leadership do not have to be opposites. America can lead by building the platform on which the world collaborates. Enrico Fermi, Migration and the Political History of Science. The Enrico Fermi displays also make the political history unavoidable. Fermi was one of the foundational physicists of the 20th century. He received the 1938 Nobel Prize in Physics and came to the United States during the period in which fascist rule and anti-Semitic laws endangered his family and distorted European scientific life. He later participated in the Manhattan Project and led the work that produced the first controlled nuclear chain reaction at the University of Chicago. The laboratory that bears his name therefore represents several intertwined histories. Fundamental physics, immigration, fascism, war, nuclear technology, American scientific institutions, the global movement of knowledge. Fermi's story is a reminder that scientific talent does not exist independently of political conditions. A country can attract minds. A country can drive them away. A government can fund discovery. A government can corrupt science through ideology, persecution or secrecy without accountability. Immigration policy is science policy. Civil rights are science policy. Education is science policy. International trust is science policy. The physical laboratory may be built from concrete, magnets and electronics, but the intellectual laboratory depends on whether talented people believe they can build a life and pursue truth here. Fermilab was established as the National Accelerator Laboratory in the late 1960s, on a 6,800-acre Illinois site chosen through a national competition. The main ring was completed ahead of schedule and under budget, and the laboratory was dedicated under Fermi's name in 1974. Over subsequent decades, Fermilab contributed to particle discoveries, astrophysics, accelerator technology, computing and work at the Large Hadron Collider, including participation in the CMS experiment associated with the Higgs boson discovery. The grounds, prairie, bison and the scientific frontier driving around the campus also reveals that Fermilab is not only a collection of concrete and experimental machinery. The laboratory occupies thousands of acres of prairie, grassland, woods, water and restored habitat. Robert Wilson brought bison to Fermilab beginning in 1969 as a symbol connecting the laboratory's scientific frontier with the history of the Midwestern prairie. Prairie restoration began in the 1970s, and the grounds have supported continuing ecological observation, restoration and education. That connection is remarkable after the Neil Smith National Wildlife Refuge encounter. At Neil Smith, I watched restored bison occupy the road and make the modern vehicle wait. Now, at Fermilab, bison and restored prairie exist alongside accelerators investigating the smallest known constituents of nature. The laboratory contains two frontiers simultaneously. One looks backward and outward into the living system that covered this region before industrial agriculture. The other looks inward into matter at scales far below human perception. Prairie roots and particle tracks are both largely invisible from the surface. Both require instruments, patience and interpretation. One reveals the hidden living infrastructure below the grass. The other reveals the hidden physical structure beneath matter. This campus therefore joins ecological restoration and fundamental science in a way that feels completely consistent with the expedition. Understanding nature does not only mean building a larger machine. It also means learning to see the systems already operating around the machine. From discovery to applications, it is reasonable to ask what practical benefit comes from studying particles that most people will never encounter directly. The honest answer is that basic science does not always know its final application in advance. That is partly the point. An experiment designed only to produce a predetermined commercial product is development, not open-ended discovery. But the instruments required for fundamental physics continually generate capabilities with broader uses. Superconducting magnets, radio frequency acceleration, cryogenics, precision measurement, radiation detection, high-throughput computing, advanced controls, vacuum technology, materials science, quantum systems, medical and industrial accelerator applications. Fermilab's applied technology programs work with industrial partners to move accelerator technologies toward uses benefiting health, security and the economy. The laboratory also trains the specialized workforce capable of designing, manufacturing, operating and repairing these systems. The impact is therefore not limited to a future particle discovery. The act of making the experiment possible changes what the country knows how to build. A detector may require a new sensor. A beamline may require a better magnet. A magnet may require new superconducting material. The material may require new manufacturing tolerances. The experiment may require new computing methods. Those capabilities can migrate outward into medicine, industry, energy, security and future scientific instruments. The scientific question pulls an entire technical supply chain forward. What a presidential stop at Fermilab means. A presidential stop here should not be a quick photograph in front of Wilson Hall. It should be an audit of America's capacity to think beyond the next election. A president visiting Fermilab should ask, how do we maintain stable funding for projects that require decades? How do we prevent stop and start appropriations from increasing total cost and driving skilled workers away? How do we train enough physicists, engineers, technicians, welders, electricians, machinists and computing specialists? How do community colleges and apprenticeship programs connect to national laboratories? How do we improve scientific visas and international participation while maintaining genuine security? How do we protect research from espionage without suffocating the exchange of ideas that make science work? How do federal procurement rules affect the speed and cost of building one-of-a-kind equipment? How do we preserve institutional knowledge when experienced workers retire? How do we maintain accelerators, cryogenic systems, buildings, power infrastructure and computing rather than funding only glamorous new construction? How do we translate technologies outward without privatizing all the gains from public investment? How do local communities participate in and benefit from the laboratory? How do we make enough of the institution accessible to students and the public that national science does not become socially invisible? Those are presidential questions because the laboratory operates on a timescale longer than one administration. The presidency has to preserve continuity between generations. A detector may be conceived under one president, funded under another, built under several more and produce its greatest discovery after all of them have left office. That makes scientific leadership an act of stewardship. The president may never personally receive the political credit for the discovery. The job is to keep the complete circuit alive anyway. This place deserves funding, and more of it. My conclusion from visiting Fermilab is straightforward. This place deserves robust, stable and ambitious public funding. Not because every experiment is guaranteed to discover a new particle. Discovery cannot be guaranteed. It deserves funding because maintaining a civilization capable of asking these questions is itself a national asset. The investment supports fundamental knowledge, technical capability, international leadership, advanced manufacturing, scientific education, high-skill employment, computing, superconductivity, cryogenics, quantum research, industrial partnerships, peaceful international cooperation. The next generation of scientists and engineers. A nation can spend enormous sums reacting to crises created by technological dependence, or it can maintain institutions that preserve its capacity to understand and build the technology shaping the future. Scientific funding should not be treated like a faucet that can be turned off for several years and restored without damage. A laboratory is a living network. The people leave. Suppliers disappear. Special tooling is lost. Students choose other careers. International partners lose confidence. Construction delays increase costs. Institutional memory degrades. Maintenance debt accumulates. The building remains visible while the real capability drains away. That is the same lesson I have found across the expedition. Construction creates the structure. Maintenance keeps the promise. Funding Fermilab means funding the people, operations and continuity that make the visible institution real. My Fermilab takeaways: the accelerator is transportation infrastructure. Fermilab changed my understanding of transportation again. Transportation does not begin at the scale of a wagon, train or airplane. Nature itself contains particles in motion, and human beings have learned to construct routes, accelerators, curves, transfer points and receiving stations for them. Speed makes geometry more important, not less. A near light speed particle still has to negotiate a radius. Greater momentum requires stronger magnetic force or a broader curve. The fastest system demands the strictest alignment and control. The complete circuit extends below the atom. Protons, targets, muons, magnets, aluminum, conversion electrons, detectors and computers form a supply chain. The particle is the payload. Its charge, energy, momentum, identity and timing are the condition that must be preserved or measured. Mu2e is searching for a hidden conversion path. The experiment is almost like a subatomic DC to DC converter, except the critical question is not ordinary operating efficiency. It is whether nature permits an extraordinarily rare direct conversion from muon to electron at all. Dune is a new transcontinental system. The railroad required tracks across the continent. Dune will send neutrinos through the continent. The Earth becomes part of the beamline between Illinois and South Dakota. Architecture affects knowledge. Wilson Hall was designed to inspire people and encourage intellectual collision. The atrium, art, offices, flags and common spaces are part of the laboratory's information transfer system. International collaboration is American power. The flags are not evidence that the laboratory is less American. They show that the United States has built something important enough for the world to join. Hosting global science strengthens national capability and peaceful international relationships. Security protects brainpower. The feeling I recognized from Lawrence Livermore was the importance of what exists behind the boundary. Security protects machinery and information, but ultimately it protects the concentrated work of people whose knowledge cannot be replaced by ordering another part. Basic science is future infrastructure. We cannot know every application before making the discovery. The attempt to answer fundamental questions produces magnets, detectors, computing, cryogenics, manufacturing capabilities and trained people that later move into the wider world. A president must defend long-time horizons. Markets and election cycles are not naturally good at protecting experiments that may require 20 or 30 years. That is precisely why national institutions and presidential stewardship matter. Closing: I began this expedition following a railroad. I learned how steel rails controlled the movement of locomotives through mountains. I learned how telegraph wires controlled the movement of information. I learned how dams controlled the movement of water. I learned how refineries controlled the movement and transformation of molecules. I learned how classification yards sorted freight. Now, at Fermilab, I am seeing how electromagnetic fields control the movement of particles below the atom. The scale changed. The system's logic remained. There is still a payload. There is still a route. There is still speed. There is still radius. There is still energy. There is still transfer. There is still classification. There is still loss. There is still maintenance. There is still a receiving station. And there are still human beings whose intelligence makes the entire invisible system work. Fermilab is not merely a place where physicists study particles. It is a national and international machine for extending the boundary of what humanity can know. A presidential candidate should come here not to pretend to understand every equation, but to understand what makes understanding possible: the people, the architecture, the funding, the instruments, the continuity, the freedom to ask a question whose answer may not arrive during your administration, or even during your lifetime. That is what serious national leadership means. You build and protect the complete circuit so that the signal can reach the future.
Yeah, when I was learning about the muon to electron conversion, that was super cool. That's why I thought about the DC to DC, and I deal with that all the time because I'm dealing with AC power generation from the car to the AC to DC to the battery, then DC to DC out, or DC to AC using the inverter and the battery backup, the EcoFlow I have. Okay, so before I came here, I was in Oshkosh, and the festival was there the 2 days before I was there. So while I was in Oshkosh, I went to the EAA Museum, the Experimental Aviation Association Museum. See all the planes that I've always been wanting to see, and it was incredible. Huge Rutan section, tons of other planes. Super cool. They spent a lot of effort talking about the different materials and things used. Now those are carbon and titanium and boron for fiberglass and stuff like that. That's super amazing and has kind of relationships on the manufacturing side. They talk about needing miles and miles of titanium niobium or something wire or something. That's super cool. And with aviation, you're going to need tons of titanium or tons of Kevlar or carbon or whatever for composites, and titanium also, and the merging of materials and things like that. But the thing is, you go down to the base elements, you go, oh, I go down to the base elements, that's how I can make stuff in the tangible world. But this is about making the smaller pieces that then make up the carbon or the materials, the titanium involved in any of this process. And it's just interesting to go even smaller in the manufacturing. Also, still staying in the experimental side of things. This is the experimental aviation where we're testing, everything from very easies to extras, extra 540s. They have prototypes, so many planes. And one of the main things about an experimental aviation museum versus a normal aviation museum is they'll be making an F4, and they'll be like, this F4 is special because this was in this blah, blah, blah. But at the experimental museum, they're one of one. That's the whole thing. With the XB70, there's only two. With the X59 or whatever, the Vista, there's only one of those. Same thing with a lot of the planes in the Experimental Aviation Museum. There's only one of a lot of those planes, each one of them, and they're very special. And it's in the whole category of experimental, and some of the CNC things and items and machining and construction work that's made for the Fermilab is also exquisite machined. It's one of one or very limited edition. I saw some of the different parts and things. And as you see, as we get to this stage of cables and lines, and you see this translation to wireless power transfer of distance, which we're just starting to get with ASA controlled array for beamforming of power transfer. So now to see that with this Fermilab concept with transferring with Dune is pretty wild. It's this evolution of technology that I keep seeing, and layers of translation. So we need roads, thinner, better, faster, stronger, more efficient. And at a certain point is, well, maybe we don't even need roads anymore. Maybe we don't even need wires or copper. And the balance of having to boost up voltage to go farther and then adapt down, or step down voltage, step down, not transform. It's the whole game of how we do things nowadays. And that's the whole game with the muon. So if we can figure that out. And then there's a whole section, they have a whole big area on quantum. And they talk about the AI also at picking out certain things and simplifying the analysis. You have tons of information, but you only need a tiny bit of information for what you're looking for, what's rare and what's special. And that's what I've said for a long time, is the hardest thing in the world is knowing what's good. And that's why I ended up going to the Fermilab. And that's why nobody else is there on a tour visit. I'm the only one. Everyone's in Chicago, busy at the Obama Museum. I mean, that'd be nice to do, but that's all $400, $700 a night hotel rooms down there. $20 parking. The museum there, if the science museum I want to go to there is $25. If I want to go there for sure, but like, I have things I'm trying to do and things that I'm worried about, and you gotta prioritize, I guess. And this seemed more appropriate and more impactful for me and for the future. I mean, there's gonna be another time I'm gonna be in Chicago and doing something, but not much time. I'm gonna have an excuse to drive all the way out to the Fermilab, so. We also don't know at a time and a place of national security where civilians won't be allowed there, so. Man, to think about all the visas and nonsense they have to go through, but how important, so much construction underneath, that's the thing. It's never done. Nothing's ever done. If it's done, then it's antiquated and they're building something new next to it or something outdated, I guess. Super cool that like 900 people were on that Higgs boson thing from CERN. It shows the interconnectedness and how, I mean, this is really the earliest bit of international bit of my president's school. More will come later, but this is really the earliest touch of that with all the flags and everything and people there. And discussion about what a project means for a site, a nation, and for the world and humanity itself. I'm hungry.
This is the missing connective tissue between Oshkosh, Fermilab, your mobile power system, experimental manufacturing, AI and President School. It should be part of the live Fermilab narration in your own first-person voice. From experimental aircraft to experimental matter. One reason the muon to electron conversion grabbed me so quickly is that I already deal with power conversion constantly in the mobile studio. The truck generates AC power that may be converted to DC to charge a battery. The EcoFlow stores that energy chemically. Then I may take DC out directly, convert one DC voltage to another DC voltage, or invert it back into AC to operate equipment designed for wall power. Every conversion has a purpose. Every conversion has losses. Every device needs a certain voltage, current, waveform and operating condition. It is not enough to possess energy in the abstract. The energy has to arrive in a form the next part of the system can actually use. That is why Mu2E immediately made me think about a DC to DC converter. The negative charge remains negative, but the carrier changes from a much heavier muon into a much lighter electron. The energy appears in a new form and has to be recognized through an extraordinarily precise receiving system. The scientific question is obviously much deeper than an electrical converter, and the direct conversion may be unbelievably rare. But my system's brain recognizes the same architecture. Input state controlled environment transformation, output state measurement, that is the complete circuit. And it connects directly to where I had just been before Fermilab, Oshkosh. The experimental scale above the human body. Before coming here, I was in Oshkosh. The major aviation festival had been taking place just before I arrived, and I went through the EAA Aviation Museum, the Experimental Aircraft Association Museum. That was incredible because an experimental aviation museum is different from an ordinary aviation museum. In a conventional museum, an aircraft may be important because it served in a particular squadron, flew a particular mission, or carried a particular person. There may have been hundreds or thousands of other airplanes of the same model. In experimental aviation, the aircraft itself may be the experiment. It may be the first one. It may be the only one. It may be a prototype created to answer one narrow question. Can this shape fly? Can this material survive? Can the structure become lighter? Can the engine be placed somewhere different? Can the controls be reorganized? Can the aircraft fly faster, higher or more efficiently? Can a completely different manufacturing method work? A one-of-one experimental airplane is not merely a vehicle. It is a physical hypothesis. Someone had an idea, converted the idea into drawings, materials and tooling, assembled it, placed a human being inside it and asked reality for the answer. That is experimental science at the scale of the human body. The Rutan section and the freedom to change the shape. The large Rutan section was especially important to me. Those aircraft show what happens when designers stop assuming an airplane must continue looking like the previous generation of airplanes. The wings can change. The tail can change. The materials can change. The arrangement of engines, passengers and controls can change. The manufacturing method can change. Experimental aviation gives physical form to the question, what part of the accepted design is a law of nature, and what part is merely inherited convention? That is also what Fermilab is asking at a more fundamental scale. The standard model explains an extraordinary amount, but scientists are constructing experiments to discover whether some accepted boundaries are incomplete. Mu2E is asking whether a muon can take a transformation route that the existing model makes almost impossibly rare. Dune is asking what neutrinos do as they move across a vast distance and whether their behavior can help explain the structure and history of the universe. In both experimental aviation and particle physics, the experiment is built at the boundary between what is already understood and what might still be possible. Materials are part of the idea. The EAA Museum spent substantial time explaining materials. An aircraft cannot be understood only through its aerodynamic shape. Its possibilities are constrained by what it is made from. Aluminum, steel, titanium, fiberglass, carbon composites, aramid fibers such as Kevlar, adhesives, foams, honeycomb structures, high-temperature materials, fasteners, wiring, control cables, transparent materials. A shape may look perfect in a drawing and still be impossible to build at the required weight. A material may be extremely strong and still be too difficult to machine, join, inspect or repair. A composite may allow a radical curve that would be difficult to produce from conventional sheet metal. Titanium may survive heat and load but create cost and manufacturing challenges. Every performance gain creates a manufacturing problem that must also be solved. That is why the aircraft in an experimental museum can be so rare. Some of them required unique molds, jigs, processes and combinations of materials. The finished airplane may be one of one because the production system was created for one physical question. Fermilab goes beneath the material. Then I arrived here, at Oshkosh. I was studying how engineers combine carbon, titanium, fiberglass, metal, resins and other materials to construct an experimental machine. At Fermilab, the investigation goes beneath those materials. Carbon and titanium are already organized matter. They are elements whose behavior becomes the starting material for the aircraft engineer. Fermilab asks about the smaller constituents and forces from which the behavior of matter emerges. The aviation designer asks, what can I manufacture from titanium? The particle physicist asks, what is matter, and what rules determine how its smallest constituents transform and interact? That is an extraordinary progression. Aircraft structural material, chemical element, atom, subatomic particle field, interaction and probability. President School had already moved from complete trains to individual rail cars, from rail cars to coal, from coal to ancient biological material, from petroleum to molecules, and now from molecules into particle physics. Every stop has taken the system one layer deeper. One-of-one aircraft and one-of-one scientific machines. Fermilab also feels connected to the Experimental Aircraft Museum because much of the equipment here is not normal commercial inventory. These are not simply machines ordered from a catalog and installed without modification. An experiment may require a uniquely shaped magnet, a custom vacuum chamber, a special target, a detector built for one narrow particle energy range, a cryogenic vessel, a precision machine support, kilometers of specialized wire or cable electronics that must function in radiation. A component manufactured to tolerances. Ordinary industry rarely requires a structure that may never be duplicated in exactly the same form that is experimental manufacturing. The scientific question creates a machine that did not previously exist. The machine requires new tooling. The tooling requires new materials and measurement. The manufacturing process itself becomes part of the research. At the EAA Museum, A one-of-one aircraft may embody one person's radical aerodynamic idea. At Fermilab, a one-of-one detector component may embody the work of hundreds of physicists, engineers, machinists and international institutions. Both are physical hypotheses. One flies through the atmosphere, the other guides or detects something far smaller than an atom. From wire to fields, this also connects to the evolution I have been following throughout the expedition. At first, transportation requires a physical road. Then the road becomes a railroad with a precisely controlled right-of-way. Information moves through telegraph wire. Electricity moves through copper. Voltage is increased for long-distance transmission and step-down near the user. Fiber moves information through light. Radio and microwave systems move information without a continuous wire. Satellites move signals across continents. Now engineers are developing more controlled methods of transferring energy wirelessly through directed electromagnetic fields and phased arrays. The visible physical route can become thinner, lighter and less obvious until the track is no longer a steel rail or copper conductor. At Fermilab, the particle does not ride on a physical rail. The electromagnetic field defines its path. The particle is traveling freely through a vacuum, but the magnets create an invisible transportation corridor. The right-of-way has become a field. That does not mean the physical infrastructure disappeared. It became more demanding. The route still requires magnets, power supplies, cables, cryogenics, vacuum pumps, alignment systems, sensors, shielding and control computers. The invisible path depends on a massive visible support system. That is a recurring mistake in how people understand advanced technology. Wireless does not mean infrastructure free. Digital does not mean immaterial. AI does not mean computation without electricity, cooling, buildings and human labor. The more invisible the service becomes to the user, the easier it is to forget the physical machine keeping it alive. Dune as transportation without a visible road. Dune may be the ultimate expression of that transition. The experiment begins with acceleration and precisely controlled beam infrastructure here at Fermilab. But the neutrinos themselves do not need a tunnel extending all the way to the distant detector. They can pass through the Earth. That is astonishing. After following roads, rivers, railroad grades, mountain tunnels, bridges and highways across the country, the Transcontinental Railroad needed workers to blast through Donner Summit. Interstate highways need cuts, bridges, snow removal and constant paving. A fiber route needs trenches, conduit and repeaters. Dune creates particles here and studies what arrives after they travel through a continent without a conventional road connecting the two experimental stations. The Earth becomes the transmission medium. It is almost a transportation system that has transcended the ordinary meaning of infrastructure, but only because the physical systems at the origin and receiving end are so extraordinarily precise. You still need the accelerator. You still need the target. You still need the near detector. You still need the enormous far detector. You still need timing. You still need computing. You still need construction, excavation, cryogenics, electrical power and thousands of people. The middle of the route can become invisible because the endpoints have become more sophisticated. Boosting, stepping down and matching systems. Voltage conversion is one of the deepest patterns in modern infrastructure. Electrical power is increased to higher voltage for efficient long-distance transmission and then stepped down so buildings and devices can use it. My truck and mobile studio repeat that entire national system at a tiny scale. The truck generates power. An inverter may produce AC. A power supply converts that AC back into the DC required by electronics. A battery stores energy at one voltage. A DC to DC converter changes it to another voltage. Another inverter may recreate AC for equipment whose internal power supply immediately converts it back to DC again. Every transition exists because different parts of the system were designed around different operating standards. The conversion allows incompatible components to cooperate. That is why the muon to electron idea felt so intuitive to me. It appeared like a transformation between two carriers with the same electric charge but radically different mass and behavior. Again, this is an analogy, not a claim that a particle interaction is literally an engineered voltage regulator. But analogies matter because they allow the mind to transfer understanding from one scale to another. The same thought pattern lets me connect voltage conversion, gear ratios, railroad transfers, aircraft propulsion, radio frequency acceleration, particle transformation, data compression, biological metabolism. Something enters, a system changes its condition, something useful or measurable leaves. The question is always what was conserved, what changed, what was lost, and whether the output can be recognized and used. AI and the rare signal Fermilab's quantum and computing material added another major connection. These experiments generate enormous quantities of information, but the scientific objective may depend on identifying a tiny number of meaningful events inside that enormous field. More data alone is not knowledge. The central problem is classification. Which event is ordinary background? Which event came from the detector behaving incorrectly? Which signal came from cosmic radiation? Which pattern came from the known physics? Which event is rare, real and potentially revolutionary? That connects directly to something I have said for years. The hardest thing in the world is knowing what is good. In filmmaking, you may have hundreds of hours of footage. The problem is not possessing images. It is recognizing the moment that contains the story. In intelligence analysis, the problem is not merely collecting more information. It is identifying the warning that matters. In medicine, the problem may be finding the small abnormality inside millions of normal measurements. In government, the problem may be recognizing the unusual failure hidden inside routine paperwork. In particle physics, the problem may be distinguishing one extraordinary event from an almost unimaginable number of ordinary ones. AI can help classify, filter and reduce the analysis burden, but the machine still needs a definition of what matters. Training, validation and human scientific judgment. You cannot simply ask the system to find something interesting and assume its confidence is truth. The expedition itself has already demonstrated that AI can widen the inquiry extremely quickly. It can also confidently identify the wrong pipeline. The future is not artificial intelligence replacing observation. It is human observation, physical instruments, computation and correction working as one circuit. Why I prioritized Fermilab. Most visitors to the Chicago region are going to the places everyone already recognizes. Those places matter. I would also like to visit the major museums in Chicago, but I had to prioritize. Hotels and parking in the city were expensive. I am operating a long expedition with limited time, money, energy and physical capacity. I also knew that I might return to Chicago for many other reasons. I did not know when I would again have a natural reason to drive all the way out to Fermilab. That made this the more consequential stop. President's School is not supposed to follow only the most obvious itinerary. It is supposed to identify the institution whose importance is larger than its public visibility. There was almost nobody else touring when I was there. That does not mean the place lacks importance. It may mean the public does not understand what it has. The easiest tourist choice and the highest value educational choice are not always the same. Prioritization is governing every decision to fund, visit, study or preserve one thing also means not selecting something else at that moment. The responsibility is to recognize what is rare before the opportunity disappears. Public access is not guaranteed forever. There was also a deeper reason to come now. A national laboratory balances public science with national security, international collaboration, controlled access and changing risk. The public areas are accessible today under the laboratory's present rules. That does not guarantee the same access forever. Security conditions can change. Construction can close areas. Projects can move. Public programs can lose funding. Buildings can require repair. An institution can remain physically present while becoming less available to ordinary citizens. I learned that repeatedly during the expedition. The museum is closed. The stream failed. The bridge exists but the train does not cross. The right exists but the procedure is inaccessible. So when a significant institution is open and reachable, there is value in physically going there. That access also creates political responsibility. The public funds much of the system. The public should be given meaningful, safe ways to understand what the system does. International science happening in front of me inside Wilson Hall. The international flags made the collaboration visible. Then I saw people who appeared to work there explaining the accelerator system to their partners or family members. That was an unexpectedly human version of international science. The laboratory was not only a list of countries on a website. People from different backgrounds were standing inside the building, transferring knowledge through ordinary conversation. One person explained the smaller acceleration stage, the larger ring and the newer branch under construction. The technical system and the human system were operating together. The scientists do not arrive as disembodied brains. They arrive with spouses, partners, children, visas, housing needs, languages, careers and uncertainty. That means visa policy is laboratory infrastructure. Housing is laboratory infrastructure. Healthcare is laboratory infrastructure. The ability of a spouse to work as laboratory infrastructure. A person may be one of the few people in the world capable of solving a specialized problem. Losing that person because the surrounding administrative system is hostile or unpredictable is not merely a personal inconvenience. It is the loss of national scientific capacity. Nothing here is ever truly finished. The continuing construction around Fermilab may be one of the most important things I saw. A person might imagine a scientific laboratory as something built once and then used. That is not how frontier science works. A machine is constructed to reach the present boundary of knowledge. It produces results. Those results reveal the next question. The next question requires a more sensitive detector, a more powerful beam, a cleaner signal, a new branch, a different target, or an entirely new experiment. If the laboratory declares itself finished, it has stopped being a frontier laboratory. Completion and obsolescence can almost arrive together. That is the same pattern I found throughout the expedition. The original railroad tunnel was completed. Then larger trains required new clearance. The bridge was built. Then operations had to be compelled. The dam was completed. Then divers had to inspect it. The highway opened. Then traffic and truck performance required expansion. The communications system worked. Then the bandwidth demand changed. The aircraft prototype answered one question and produced the next design. The particle experiment reaches one sensitivity and begins exposing the next boundary. A living institution is never done. It moves among construction, operation, maintenance, correction and replacement. The Higgs collaboration and distributed discovery. The material concerning Fermilab's participation in the Higgs boson research made the international network even clearer. Hundreds of people from Fermilab were connected to the larger CERN collaborations. A discovery associated publicly with one facility may depend on researchers, detectors, software, manufacturing and analysis distributed across many laboratories and countries. There is no single heroic scientist standing alone at the moment of discovery. There are thousands of handoffs. Someone designed a sensor. Someone fabricated a component. Someone calibrated the detector. Someone maintained the cooling. Someone wrote reconstruction software. Someone checked the statistics. Someone challenged an error. Someone trained the student who noticed the anomaly. Someone preserved the funding long enough for the result to arrive. Scientific discovery is another complete circuit. What this changed in President School. This may be the earliest point in President School where international collaboration became physically unavoidable. Earlier parts of the journey examined national systems. The Transcontinental Railroad, federal land grants, state and local government, interstate highways, public dams, national laboratories in the United States, military infrastructure, national wildlife restoration. Fermilab demonstrates that some modern systems cannot be understood or operated only as national systems. The laboratory is physically in Illinois. The funding and responsibility are strongly American. The knowledge network is global. The equipment, expertise and analysis cross borders. The discovery belongs to humanity even though particular nations decide whether the infrastructure exists. That creates a more mature meaning of national leadership. Leadership is not only possessing the machine and excluding everyone else. Leadership can mean building the trusted platform on which many nations perform work no single nation could accomplish alone. That is power through coordination. It is scientific diplomacy made physical. My expanded takeaway: Oshkosh and Fermilab belong together. At Oshkosh, I saw experimental machines designed to move through the atmosphere. At Fermilab, I saw experimental machines designed to move and identify particles below the atom. At Oshkosh, rare aircraft showed how shape, material and manufacturing can test the limits of flight. At Fermilab, rare scientific instruments show how magnets, vacuum, cryogenics, targets and computation can test the limits of the standard model. Both depend on one-of-one construction. Both depend on exceptional machinists and engineers. Both require acceptance that failure can produce knowledge. Both transform an idea into a physical object and ask reality whether the object works. Both show that invention requires manufacturing infrastructure. And both demonstrate why a country must preserve institutions where people are allowed to attempt things that do not yet have guaranteed commercial returns. The experimental aircraft asks, "Can this machine fly?" The particle experiment asks, "Does nature permit this event?" The national question is, are we still capable of building the machine required to find out? That is what my stop at Fermilab means. I did not come here because it was the easiest attraction. I came because President School requires learning how the future is physically constructed. One prototype, one magnet, one detector, one international collaboration and one rare signal at a time.
Alright, thanks everybody. That was a quick stream. Gotta catch up on my stuff and take a break. Again, thanks all. This has been great.